All right, next we have example 1. They give us a vector field, capital F, and we are asked to verify that this scalar function is a potential. So let's go ahead and do that. So for part A, to verify that this is a potential for f, all we have to do is take the gradient of it and show that it does equal capital F. So the gradient of this function, the x partial is 2xy plus z, the y partial is x squared, and the z partial is x, which does, in fact, match the given vector field. So we can conclude, therefore, capital F is conservative and has potential F. So that's done. For part B, we are now asked to evaluate a line integral where C is a path from the point P to the point Q. So it's a curve from P to Q. So this doesn't tell us anything about this path. We could go from P to Q in a way that's very loopy. We could go from P to Q that is a straight line. But because we're not given the actual information, we can't say for certain what that path is. We're not allowed to just assume it's a straight line, because all it says is it's a curve. It could be anything. Because we don't actually know what the curve is, we can't actually go ahead and try to write down some sort of parameterization for this, because we don't know what the path is. So forget about trying to do that. There's no chance of us being able to do that since we don't know what the path is. There's an infinite number of paths that begin at a point P and terminate at a point Q. So instead, this is trying to get us to think of the above theorem. Theorem 1, the fundamental theorem for conservative vector fields. Anytime that you're asked to calculate the line integral, but they don't give you a particular path, or they only give you the endpoints, there's a good chance that the vector field's conservative, and that's how you should be approaching the problem. So, in this problem, they gave us the potential function. We verified that it was a potential function, which in the process allows us to conclude that the vector field is conservative. So what this means is the integral over the path C, f dot dr, so this is part B, is exactly the same thing as the line integral over the gradient of that given function f dot dr. And by the fundamental theorem of conservative vector fields, we can write this down as f, our potential function, at the final point minus f at our initial point. So then we can just plug in the values. So f of 2, 2, 3 minus f of 1, negative 1, 2. Which we'll go ahead and use our function f to get, again, our function f is just right here. So we should get 8 plus 6 minus negative 1 plus 2. So this is 13.